All right, so we're going to start with number 2. So these say to find the points of continuity and the points of discontinuity of the function, and then identify each type of discontinuity if there are any. So number 2, we have y equals x plus 1 over x squared minus 4x plus 3. So I need to decide if this is continuous or not. Any guesses without us doing anything?
Yes.
Okay. Anybody? I mean, I'm just asking before we do work if you think it's going to be continuous or not. Anybody else want to guess?
Continuous.
Okay. Okay, so we're going to find out. So I'm going to factor the bottom.
Oh, wait, no.
Okay, I'm going to factor the bottom. So what would the bottom factor into? Yep, x minus 1, x minus 3. And then I'm going to set that equal to 0. Okay, if it would cancel with anything on top, I'm going to cancel it, but obviously that doesn't. So I'm set it equal to 0. So x is equal to 1, x is equal to 3. So these are going to be points of discontinuity. Okay, because they cause a problem. Okay, so those are going to be vertical asymptotes basically in the graph. All right, so now that we've said that there are points of discontinuity, any guesses to what kind of discontinuity this is?
Jumping.
Jumping is going to pretty much always look like a step function.
Infinite.
All right, so this one's going to be infinite. In, I don't want to say 100% of the cases, but in most cases, if it's a fraction, it's going to be infinite. Okay, because of the way that it's going to graph with the asymptotes and stuff. So this is going to be infinite discontinuity. Now, I will tell you that there are going to be times where one point may be one type and another point may be another type depending on what they are. But like these are both on the bottom, so you can pretty much guarantee these are both going to be infinite. Now, you could graph it and actually visualize it, but basically as it gets close to that, it's going up to like infinity or negative infinity depending on, I don't know what that graph looks like off the top of my head, but I can wager just by the fact that it's a fraction and has variables on the bottom that it's going to be kind of like that one that we did a little bit ago. So, let's see. Number 4. Y equals the absolute value of x minus 1. Is this continuous? Nathan says yes.
Sure.
Peyton says yes. Well, there's 10 problems in this section. What does an absolute value function look like? A V, okay. Are there any gaps in it? Nope. Okay, so it is continuous. So, the book says none because there's no points of discontinuity. So, but if you just write continuous, then I'll know what you mean by that.
Oh, because is it asking how many points of discontinuity? Continuity?
Yeah.
Sorry.
Let's see. Alright. Not a lot of good examples that are even. But we'll get more of the discontinuity stuff in a little bit. Alright, next thing, number 20. These say find each point of discontinuity and which of the discontinuities are removable, not removable, and then give reasons for your answer. So, that was nice. 20. F of x is equal to 3 minus x when x is less than 2. 2 when x is equal to 2, and x over 2 when x is greater than 2.
Right.
Oh, I didn't draw the
I don't
thing
like that.
long enough. Darn it. It's a little dumb now.
All right, so the first thing is it wants us to find each point of discontinuity. And then I was like looking at the wrong problem for a hot second. And I was like, I wrote the problem wrong, but that was the wrong one. Okay, so what we're going to do is we're going to look at the limit from the left and from the right and then the two-sided limit, okay, and see what those are equal to, and then we'll go from there. So the limit as x approaches 2 from the left of 3 minus x, okay. Now, you're probably like, why did she pick that one? Anybody curious why I picked 3 minus x?
It's gonna do something nice for you.
Or does anybody know why I chose that one? Do you, or want to guess why I chose that one?
Maybe positive?
I'm looking at 2 from the left.
Oh, so you gotta pass 3 first, right? Wait, what?
Wait.
Ignore this.
No.
I want 2 from the left. So that would be where x is
Oh! Wait.
less than 2.
Yeah.
Okay, where x is less than 2 would be 2 from the left, so that's why I chose this one. Okay,
Makes sense.
are we following? We tracking? No?
No.
Alright, so x is less than 2. Okay, so 2 is right here, so x is over here, right? So 2 from the left, coming from the left, that's going to be this one. So those go together.
Okay.
They go with what's beside them. It's a little easier when you see it actually written on a line versus just, in blank space. But, so if I were to put in something like 1.999999, okay, because that's on the left side of 2, as close to 2 as I can get, what is that going to approximately give me? 3 minus 1.999999. 1. Okay. Now the next thing, the limit as x approaches 2 from the right. Anybody want to guess which one goes with this one?
X is greater than 2.
Yep. So x over 2. So this is like 2.0001, something like that. So what would that give me? 1. So then the limit as x approaches 2 of f of x should be equal to what?
1.
1.
Nice.
But what is f of 2? So I plug in 2 for x. What is it equal to, according to what's written on my function that was given to me? X equals 2. So f of 2 is supposed to be equal to 2. Okay, or it is equal to 2 we were thinking it should be 1. Okay? So according to what was given, so everybody's tracking, if I plug in x for f of x, or sorry, 2 for f of x, words. If I plug in 2 for x and f of x, it should be equal to 2. Okay? So, f of 2 is equal to 2. However, the limit as x approaches 2 of f of x, we said was equal to 1. That's not equal to f of 2. So it is discontinuous at that point. So it's discontinuous at x is equal to 2. And so then the second part, which of the discontinuities are removable or not removable, and then give the reason for your answer. So part B would be removable at f of 2 is equal to 1. So basically, if you graphed this, you'd pretty much end up with a hole, okay, in your graph, because the two-sided limit is 1, so it should be equal to 1. But at 2, there would be just basically a point on the graph at 2. So at x is equal to 2, there would be a point at y equals 2. Basically, if you were to visualize that, okay, which makes it removable. Let's see. I think I'm going to go ahead and stop there. We might do one more of these tomorrow. There's also one that has some pictures with it, so maybe we'll do one that has the picture with it, because sometimes I think it's easier to visualize when you see the picture. So we may start with the stuff that has pictures tomorrow, because that I can't really record because I've got to put it underneath, like where you can see the book. And then there's a few more that we'll look at, 26 through 34-ish, that want the extended continuous function and stuff with theorem 7. So we'll look at that. I might also try to see if I can find an intermediate value theorem problem, because they talk about it in this section, but I don't even see a problem that goes with it, so maybe it's coming later, I don't know. But I feel like if they talk about it, there should be a problem that goes with it. But I don't see one. So, anyways, we'll look at that tomorrow, but there's only a few minutes left, so that way y'all can just chill for a minute.